Swayam Prabha. Digital India. Educated India.
Okay, so our last speaker is Chao Liu.
Yeah.
The topic will be feasible path-based branch and bound algorithm for strongly non-convex MINLP problems. So Dr. Chao Liu,
Yeah.
over to you.
Can you hear me now?
Yes, I
Oh,
can.
great, thanks. Thanks.
Visible.
Yeah. Hello, everyone. My name is Chao Liu. I'm from the University of Manchester, and I'm really glad to present my work here today. So my research is about a novel algorithm for solving strongly non-convex MINLP problems in optimization-based process design. Sorry. So process design, there are usually three major approaches in process design, including evolutionary method, decomposition-based method, and optimization-based method. And here we only focus on the optimization-based process design, as it provides a systematic framework for process synthesis and possesses the abilities to screen numerous process configurations. And many optimization problems arising in process design are usually modeled as mixed integer nonlinear programming MINLP problems. And the integer variables can be used to make discrete decisions such as selection of process equipment or assignment of tasks. It's also possible to introduce discrete quantities, such as number of trees in a distillation column, and different from MILP, the objective function and all the constraints may be convex or non-convex. So the coupling of the integer domain and the continuous domain, as well as the associated nonlinearities and non-convexities, make MINLP problems extremely difficult to solve theoretically, algorithmically, and computationally. The reason we are working on this is that through this, we can change the traditional chemical processes into more sustainable processes by using process synthesis, process integration, and intensification, and achieve the triple dimensions of sustainable development. And here are the three common unit models used for process design. Shortcut models are based on simplified assumptions, such as constant molar flow in a distillation column, and they show very good convergence. However, accuracy is compromised, and the results may be impractical to the real industry process. Surrogate models can be easily plugged into process simulator. The drawback is really computational intensive. Multi-runs are required to get a proper result. The last one is regress model. The model we prefer is very accurate, though it's time-consuming and difficult to converge. So later, I'm gonna explain how we address the convergence difficulties. The objective of this work is to develop a novel branch and bound algorithm to solve the aforementioned problem. This novel algorithm is called feasible path-based branch and bound algorithm, coupled hybrid steady state and time relaxation-based algorithm. So I'm not gonna say it again, so let's call it FPBB for short. Now here comes the solution approach. For your better understanding, I think I should introduce the implementation first. The NLP subproblem to be solved at each node are decomposed into two layers. The outer layer is a small optimization problem, while the inner layer is a process simulation problem. In this work, the process flowsheet models are written in the equation-oriented modeling environment, Aspen Customer Modeler, ACM. And for simulation in the equation-oriented environment, the most widely used method for solving these problems, however, is Newton method. It works best only when the starting point is near to an optimal point. The FPBB algorithm is implemented in Python, and open source optimizer SLSQP is the selected NLP solver for the outer layer optimization. Information such as derivatives and iterative values of variables transferred between Python and ACM is via ACM automation interface. Next, I want to talk about the models used in the process simulation. In unit operation model slides, we mentioned the rigorous model. You may wonder, so this is the rigorous model for distillation. It's built on mesh equations. It consists of material balance, equilibrium relation, summation equation, and energy balance. So this is the standard one. Now we modify the equations a bit, because we mentioned that for simulations in the equation-oriented environment, the convergence strongly relies on initial point. To resolve such problems, we adopt the pseudo-transit continuation modeling approach, the PTC approach, which is based on reformulating a subset of algebraic equations of the unit model into ordinary differential equations, ODEs, which leads to a new unit model described by the differential algebraic equations, DAEs. I highlighted them in the red rectangles. The original mass and energy balance equations are converted into differential mass and energy balances by prepending a time derivative term in the appropriate dependent variable, such as accumulated amount that holds up of mass or energy. The solution from dynamic simulation of DAE models by integrating accurately in time provides a close initial guess to the steady state solution. A larger basin of initial conditions is achieved. Then when changing to the steady state simulation, the solution can be easily found. We use bypass efficiency method to optimize the number of stages in a distillation column, and the bypass efficiency for each tree is defined as the ratio of non-bypassed flow to total flow. They are treated as binary variables, and in the final optimal flow sheet, they should be either 0 or 1. The summation of them equals to the optimal number of stages. Okay, so we have explained the models. Now we move on to the algorithm. So feasible path-based optimization algorithm. In the MI-NLP mathematical model, equality constraints can be divided into two groups. One group constrain the unit operation models, such as mass and energy balances, equilibrium relationships denoted as H1, while the others are denoted as H2, is a full space model. If partitioning continuous variables x into two sides, independent variables xi and dependent variable xd, the dimension of xd is equal to that of H1, as xd can be expressed using an implicit function of xi. Substituting the implicit function into the model, a feasible path-based MI-NLP problem can be derived in the model in the middle. Since the equality constraints H1 can always be satisfied, they can be eliminated from the problem, and then a full space model can be translated to the reduced space model. So our previously proposed hybrid feasible path optimization algorithm, as shown in this figure, is employed to solve the NLP subproblem at each node. It's a combination of steady state simulation and the PTC simulation. The main idea of the hybrid algorithm is that a steady state simulation is performed first. Only when it fails, a PTC simulation using tolerance relaxation integration method is then constructed. I'm not going to go to details for this due to the time limitation. And the branch and bound search tree constructed by FPBB algorithm is illustrated in the right figure. The root node is denoted as N0, at which an NLP problem is to be solved. This NLP problem is a relaxation of MI-NLP problem with all the binary variables relaxed to be continuous variables between 0 and 1. At the root node, only root node is contained in the active node site. The fixed binaural site YF0 is empty, while the relaxed binaural site YR0 contains all the binaural variables with assigned initial values that need to be determined. And the upper bound FUB is set to infinite. After solving the root node, the optimal results in YR0 star shall be examined. If all the determined values are already 0 or 1, the algorithm should be terminated with the integer solution from the root node. Otherwise, two child nodes are created. The active side will be updated with two new nodes, N1 and N2, with N0 deleted from it. At each node Ni, our previously introduced hybrid steady state and time relaxation-based optimization algorithm is employed to solve the NLP subproblem. After solving the NLP subproblem at node Ni, the pruning rules shall be applied. If there is no feasible solution at node Ni, then this node is pruned. If an optimal solution Fi star exists, it shall be compared with the upper bound FUB, which is either infinite, meaning no optimal integer solution so far, or current best integer solution. If Fi star is larger than FUB, the node will also be pruned. Otherwise, YRI star shall be checked. If all the components in the YRI star are binaries, it means solution at node Ni is an optimal integer solution. Then FUB will be updated to Fi star. If some components in YRI star are still fractions, node Ni will be treated as parent node and further branched, where one relaxed binaural variable in YRI star with value close to 0.5 is selected and forced to 0 or 1. Hereby, two child nodes Nj and Nk will be created. Obviously, only one binaural variable in nodes Nj and Nk is different from their parent node Ni. Hence, the optimal solution from parent node is used to initialize the NLP subproblems in its child nodes. So we use it. Sorry, my kind of stuff. Okay. We use it to solve the dividing wall column design cases. A distillation column with one longitudinal partition were welded to the column walls, known as a dividing wall column DWC, allows for significant energy savings as well as substantial capital and space savings. The reason for requiring significant less energy is the avoidance of remixing of internal streams. The design of a dividing wall is more complex compared to a conventional distillation column due to the increased number of design parameters as shown in the left figure. These design parameters include the reflux ratio, reboiler duty, and the number of stages in 6. Hello? Yeah.
Can you wind up in 2-3 minutes?
Yeah, sure. In 6 sections, and the set jaw flow rate. Since the number of stages is an integer variable, the optimization of a dividing wall column is an MI-NLP problem and remains a challenging issue as no dedicated software is available at this moment. So we use FPBB algorithm to solve a DWC example for the separation of a ternary mixture, and the optimal solution is obtained within 1 hour. It can be observed that the configuration obtained by using FPBB is very similar to the configuration in the literature. The method used in the literature is a special procedure which requires shortcut models to determine the initial design parameters of DWC and followed by equilibrium stage simulation, molecular tracking application, and finally use many simulations to investigate the effects of varying parameters in the flowsheet to find an optimal design. So the design procedure is tailored and computational intensive for the design of DWC. And in conclusion, a DWC example is solved to evaluate the robustness and performance of proposed algorithm and demonstrate that the proposed FPBB algorithm was able to find a locally optimum with very good convergence performance. The other superiority of our algorithm is the robust initialization procedure. Initial points are easy to choose and convergence can be guaranteed. In the future, we will try to foster the use of this novel MINLP algorithm for more comprehensive process design problems, such as synthesis problems with superstructure coupled reactors and separators, and other process intensification applications, such as reactive distillation and membrane reactors. And in the meanwhile, we will try to improve the solution quality of MNLP algorithm and make efforts on finding the global optimum within an acceptable CPU time. Thank you. Thank you for your attention. Yeah.
Thank you so much for a very good presentation. So is there any question for Chao?
Thank you for the very nice talk. I actually have 3 questions.
Oh, great. Thank
so,
you.
So the first question which I had was, how is your algorithm different from like a local MINLP solver like DICOPT or SBB? So what are you doing different from that? Like I could probably use a multi-start heuristic and couple it with the DICOPT or SBB and try and initialize my model. So I just wanted to see how different or why this, how this is different from that. The first question.
Yeah, you mean the FPBB different from SBB, right?
Yeah.
Yes, because usually we write our models in games or other platforms, right? Then we use SBB to solve them. However, for these high non-convexity problems, we usually to have very good initial points to find to look for a solution, an optimal solution, right? But the difference is that FPBB is implemented in Python, and our models are not written in GAMS. It's written in ACM, an equation-oriented environment, and we reform our mesh equations to this kind of DAE equations, from algebraic equations to DAE equations, so that we don't need very good initial points.
Okay, so
yeah, so we can increase the initial point basin, and we can find an optimal solution quite easy.
Okay.
Yeah.
So that brings me to my second question. Actually, good that you
Yeah.
brought up this slide. So you said you're solving an MINLP. So MINLP is usually only algebraic equations, but you showed your differential algebraic equation system. So I was a bit confused whether you have solving a DAE system or a MINLP problem. I was a bit confused about that.
Yes, because if we directly solve algebraic equations, it can be quite tricky, right? So for the simulation part, because our problem can be decomposed into 2 layers. So the inner layer is a process simulation problem, and the outer layer is optimization problem. So if we can't not directly solve this kind of algebraic equations, we can run we can run the PTC simulation. So use DAEs like a dynamic simulation.
Okay.
So as long as we integrate with quite accurate time, then we change to steady state simulation. Then is the algebraic. Then we solve the algebraic equations, so we can get the results more easily.
And my final question Can you comment on how well your algorithm would scale with the increase in number of binary variables?
Sorry, say again.
Can you comment on how do you think your algorithm would scale when the number of binary variables in your model would increase?
It's quite okay because for this DWC, right? For these DWC examples, we use bypass efficiencies and they are binary variables. And for these 6 sections, there are total 180 binaries.
Yeah, so my question is, what if you have like 300 or 500 binary variables in your model? Will your algorithm scale?
I haven't solved such problem with like more than 500 binaries, but so I cannot say it for sure, but I think it still can cope. The only tricky part is the CPU time.
Okay.
So we are still working on try to decrease the CPU time. You see, yeah.
Okay.
Yeah, because the inner level is a process simulation problem. And if we cannot directly solve the algebraic equations, we have to switch to dynamic simulation, which costs us a lot of time.
Okay.
So, yeah, thank you.
So, Chao, I have just one question, last question. So,
Yeah.
innovation from the previous question, what the audience has asked. So see, you are using branch and bound typically scales exponentially. And as the size of the problem is going to increase, your algorithm is going to take in exponential time.
Yeah,
Also, you are relaxing the MINLP to NLP.
correct. Yes,
So
correct.
that means the optimum solution, what you are getting is the approximate solutions.
Say again, sorry.
So the optimum solutions you are getting are the approximate solutions because you have relaxed the model. Can we say that?
Yes, that's how branch and bound algorithm works. So for it solves each node as a relaxed NLP problems. Yeah.
Okay, so what I was trying to ask you is, instead of using this branch and bound type of exact algorithms, maybe meta-heuristic algorithm will scale linearly or even polynomially.
Sorry, say again.
Maybe meta-heuristic algorithms like GA, differential evolution, etc. They can scale linearly or polynomially, even though the formulation is non-linear.
Yeah.
So, and near optimum solution you can obtain, isn't it, with a reasonable time?
I don't think using GA algorithm or the other algorithm can solve this problem at a reasonable time, because in other research group, they try to adopt a GA algorithm. It may take much longer time than this.
Okay.
Yeah.
So,
So because GA algorithm is like a stochastic algorithm, right?
yes, but then they have the advantage that you don't have to, change the differential equations. You can directly go ahead with the differential equations and solve the model.
Yes, but it also have to fit many evaluations.
Yes, correct.
Yeah, correct, right? Because using branch and bound and using SLSQP, the open source optimizer in Python, is a deterministic algorithm. So it employs the first derivative. So I think it behaves much faster than stochastic algorithms.
Okay. Okay,
Yeah.
Chao, thank you. Thank you for your
Thank you so much.
Okay, so let us thank the speaker one more time. Thank you, Chao. Thank you so much.
Thank you for your time.